Hi, welcome to this lesson on differential equations. By the end of this lesson, you should be able to work out questions like this, so stay tuned. Right, so let's have a look at a harder one on differential equation. So again, the first step is done for us. We have single term on the left hand side and single term on the right hand side. So we can begin the process of separation of variables. Now, if we look here on the right hand side, we have x multiplied by tan y. So we can put a bracket around the tan y here, or a circle around the tan y. This is in terms of y, which needs to go across to the left hand side through division. And if you look on the left hand side, we have the dx and we have the bracket here that has 1 plus x squared. So we have to move the dx and this bracket across to the right hand side. But I'll do that on the second step. So if we move the tan y to the left hand side, by dividing by tan y or multiplying by 1 over tan y, we will have 1 plus x squared multiplied by dy dx equals to x. So we just done this bit here. Now we have to move the dx as well as this bracket across to the other side. Now to move the dx, we will have to multiply. But this 1 plus x squared is already multiplying on the left hand side. So in order to move that, we have to divide. So what we have is 1 over tan y dy remaining on the left hand side. And on the right hand side, we're going to have x over 1 plus x squared multiplied by dx. Now 1 over tan y can be rewritten as cot of y dy equals to x over 1 plus x squared multiplied by dx. Separation is done. We can now integrate both sides of this equation. Now the integration of cot y is given in the formula booklet. If we integrate cot, you get the ln of sine y equals to, and then if you integrate the right hand side, here we are integrating a fraction. The first check I always do is to check if the denominator differentiates into a multiple of the numerator on the top. That's the first check I normally do. If it does, then obviously that tells me that it must be an ln one. Here, if we differentiate the denominator, we get 2x, and we have a multiple of that on the top. So what that means is that it's the ln one. It's going to be the ln of 1 plus x squared. But if we differentiate this, we get 2x on the numerator. So the adjustment needed is multiplied by a half. And don't forget, you're going to get a plus a constant c. If all the terms on the left side have an ln, and all the terms apart from the constant is an ln term, then the neat trick we can do is that we can redefine that constant c and call that the ln of a constant k. So in other words, we have an ln of sine y equals to half times the ln of 1 plus x squared plus an ln of a constant k. Now the reason I've done this here is because if all of the terms are ln's, we can use the laws of logarithm to simplify this expression further in order to get maybe sine y as a subject. So if we carry on this side here, we have ln of sine y equals to the half here as a coefficient. I'm going to move that to the power of this expression here. So it will be equal to the ln of 1 plus x squared to the power of a half. Because the rule with ln or log is that the coefficient can always be put as a power on the top. Plus the ln of a constant k. Now the next step is to, if you look at those two ln terms, this is like saying ln a plus ln b is the same as the ln of a multiplied by b. If you use that rule for logarithm, we can rewrite this as the ln of the product of those expressions inside of the ln. So 1 plus x squared to the power half times k, or k multiplied by 1 plus x squared to the power half And on the left side, we can have the ln of sine y. Now both sides have an ln. We can then e both sides, the ln's will get cancelled off. So we will have sine of y equals to k multiplied by 1 plus x squared to the power half. Now here we have sine y as the subject. If we are required to write y as a function of x, we have to do the inverse sine, and that's the arc sine of k bracket 1 plus x squared to the power half, and we now have the general solution to this differential equation. So let's move on to example 7. Given that y equals 3 when x equals 4, find in the form y equals f of x the particular solution of this differential equation dy dx equals to 3x over 5y squared. Okay, so this is the differential equation we need to solve. Now when we solve this differential equation, we will get a general solution. We then substitute in the boundary condition given here, and the solution will then be the particular solution to the differential equation. Let's start with the equation itself. Step 1 is already done. We already have single fraction on the left hand side, single fraction on the right hand side. We can now perform the separation of variables. Again, we can take the y squared to the left hand side, or we can take the whole 5y squared across to the other side. Here, this is 5y squared is dividing the numerator, so on the other side we're going to multiply by that. So we will have 5y squared dy dx equals to 3x, and then multiplied by the dx. So we have 5y squared dy equals to 3x dx. We are now ready to integrate both sides. So this side will give you y to the power of 3 divided by 3, or 5 over 3, equals to x to the power 2 divided by 2, or 3 over 2 as a constant, plus c. This is your general solution, okay? But we are asked to find the particular solution to this equation. So we need to now substitute in the boundary condition to find what that c is. You can substitute the boundary condition at the earlier stage, which is now, or at the later stage. But it's much easier if you do it at an earlier stage. So at the earlier stage, we're substituting this in. So when x equals to 4, y equals to 3. Right, so we now substitute in our boundary conditions. So when y equals 3, 3 to the power 3 is 27. 27 divided by 3 is 9. 9 times 5 is 45. So we have 45 equals to x squared. X is 4. So 4 squared is 16. 16 divided by 2, 8. And 8 times 3 is 24. Plus c. So this gives us c is equal to 21. So this gives us the particular solution. 5 over 3 y to the power 3 is equal to 3 over 2 x squared plus c, but our c is plus 21. Now we are asked to write y as a function of x, so we need to move that fraction across the other side. We're going to multiply both sides by 3 over 5. So we have y to the power 3 equals to, so 3 over 2 times 3 over 5 will give us 9 over 10 x squared, plus 21 times 3 over 5. So 3 times 21 is 63 over 5. Therefore, y will be the cube root of 9 over 10 x squared plus 63 over 5. And this is the particular solution to this differential equation. And if you prefer to write it as a index form, y would be bracket 9 over 10 x squared plus 63 over 5. And the cube root is the same as power 1/3. Okay, so the final example. Find the general solution of the equation dy dx is equal to, so minus 3 y minus 2 all over the two brackets 2x plus 1 multiplied by x plus 2. So we begin by writing down the equation. Again, the first step is done for us. Single fraction on the left hand side, single fraction on the right hand side. We have to move the y's across to the left hand side. Now the y is inside the bracket y minus 2. So in order to move that y, we have to move the whole bracket here to the left hand side. And if you do that, we have to divide on the left hand side, because on the right hand side is on the numerator of a fraction. So when you divide by the bracket y minus 2, we will have 1 over y minus 2 dy by dx equals to minus 3 over 2x plus 1 multiplied by x plus 2. And now we have to move the dx across to the other side and multiply. So we have the variables are now separated. We can now integrate the left side with respect to y, integrate the right side with respect to x. Now, the left-hand side is a straightforward integration, because if we differentiate the denominator with respect to y, we get a 1, which is what we have on the top there. So that kind of tells us that the left-hand side is going to be the ln of y minus 2. Now, the right-hand side, on the other hand, is the integration of a fraction. If you look on the right hand side, if it's a fraction, I normally check that if you differentiate the denominator, you get the numerator. But in this case, I'm not going to even try, because we can see that if you were to expand this side, we'll give you a quadratic, and the quadratic doesn't differentiate to give you a constant. Now, if your fraction is written in such a way that the denominator is factorized, or it can be factorized, then that kind of points towards partial fractions, because if your denominator is factorized, then you can split those up into smaller fractions called partial fractions. So I'm just going to write this as, for now, write it as an integration of a over 2x plus 1 plus b over x plus 2 with respect to x. And obviously, to get the a and b, we have to do the partial fraction of this. Let's now write minus 3 over 2x plus 1 multiplied by x plus 2 as a over 2x plus 1 plus b over x plus 2. So that's the same as minus 3 equal to a multiplied by x plus 2 plus b multiplied by 2x plus 1. So if we let x equals to minus 2, we get minus 3 equals to, well, that goes away. 2 times minus 2 is minus 4. Minus 4 plus 1 is minus 3. We get minus 3b. In other words, b is equal to 1. If we now say x equals to minus a half, so we can see here that 2 times minus a half is minus 1. Plus 1 is 0, so that goes away. Right, so when x equals minus a half, we get minus 3 equals to, well, this goes away. So we get minus a half plus 2, which is 1.5, or in other words, 3 over 2a. That gives you a equals to minus 2. So the right-hand side becomes the integration of, I'm going to write this fraction first because b is positive. So we have 1 over x plus 2. And then we have a as minus 2. So it's going to be minus 2 over 2x plus 1 dx. If we now check that the denominator here differentiates into a 1, which is in the numerator. If you differentiate the denominator here, that gives you 2, and we have a 2 on the top. So basically, both of them are going to be ln terms. So this will be equal to the ln of x plus 2 plus, well, not exactly plus, but I'm just going to write this as the ln of 2x plus 1 here. If we differentiate this, you're going to get positive on the top, but we want a negative, so I need to put a negative sign there. Plus a constant. Okay, so plus a constant. I'm going to put a question mark there. Now, if you go back now, so the left-hand side is an ln term. The right-hand side both of these terms are ln terms. What's the trick here? If all the terms are ln terms, how can we write the plus c as? Well, I'm sure by looking at the previous example, you would know that it'd be easier to manipulate this expression if you write this as the ln of a constant k. Right, so I'm just going to rub off the board for more space, but I'm just going to write the last line on the top. Right, so this is our general solution. Obviously, we can simplify this, but at this point, I'm just going to label it as a general solution. So in effect, we have part A completed. Now, for part B, we are now required to work out the particular solution because we're given boundary conditions. So when x equals to 1, y needs to be equal to 4. We're going to substitute this into the general equation in order to work out what that k is. So if we do that substitution, we will get the ln of y minus 2, in other words 4 minus 2, which is 2, equals to the ln of x plus 2, x is 1, 1 plus 2 is 3, minus the ln of 2x plus 1, so 2 times 1 is 2, plus 1 is 3, plus the ln of k. So here, the ln 3 cancels the ln 3 there. So in other words, ln 2 equals to ln k. That kind of gives us that k is equal to 2. We now have ln of y minus 2 equals to the ln of x plus 2 minus the ln of 2x plus 1 plus the ln of 2. So this is in effect your particular solution. Okay, but I may have left this bit out earlier. So for part B, we need to write what y is as a function of x. So in other words, we need to simplify this and make y the subject. Now, here all the terms are ln terms, so we're now going to use the laws of logarithms in order to simplify the right-hand side. The first law that we're going to look at is what happens when you have ln of a minus ln b. We can rewrite this as the ln of a divided by b. So here, if we apply this here, we can have ln a here minus ln b. So we can rewrite those two terms as the ln of x plus 2 over 2x plus 1 plus ln 2. Now we have two ln's added together, so ln a plus ln b. The rule is that we get ln of a multiplied by b. So here we can rewrite this as the ln of 2 bracket x plus 2 all over 2x plus 1. And the left hand side is ln of y minus 2. Now we have both sides as single ln terms, so we can e both sides to cancel off the ln's. So we have y minus 2 equals to 2 bracket x plus 2 over 2x plus 1. So therefore y equals to 2 bracket x plus 2 over 2x plus 1 plus 2 as our particular solution where y is the subject. In an exam, you may be given the answer to the equation. Maybe it could be equal to this, where you have to write down what the values of those missing constants are. So if you look at our solution and look at what it needs to be written in the form as, now there's two ways we can do this. One way is obviously to use long division. The other way is to just manipulate this expression there. So we have 2x plus 4, we have dividing by 2x plus 1. Well, 2x plus 4 is the same as 2x plus 1 plus 3 over 2x plus 1 and then plus 2. You can see here that we have 2x plus 1 plus 3, but 1 plus 3 gives back our 4 there. Why did I split this up as 1 plus 3? It's because now the 2x plus 1 here matches the 2x plus 1 on the denominator. We now have two terms on the top being divided by the same denominator. So 2x plus 1 divided by 2x plus 1 gives you 1 plus 3 over 2x plus 1 plus the 2 there. So therefore y equals to 1 plus 2 is 3 plus 3 over 2x plus 1. And we can see that both a and b are equal to 3. Hope you have enjoyed the lesson, so I'll see you in the next video.